Hi everyone, thanks for tuning in. Today we'll be talking about reinforcement learning and the basics of training it. We will play around with environments available through this wonderful package called Gym. Each one of these environments is a kind of game, such as Moonlander here, where there's an object, such in this case, it's to land our Moonlander correctly in between these flags without crashing it. There are lots of other games available, and if you want to explore these, you can actually just plug in the code and the framework that we're talking about today with some slight modifications and play any of these games that you're interested in and train an agent to play these games in particular. Okay, before we jump into the particular game that we'll be talking about today, I wanted to refresh briefly the key ideas that we're going to be using today to train a reinforcement learning framework. I will assume some familiarity with reinforcement learning and the reinforced algorithm. If you aren't familiar with them, then I would strongly suggest checking out Chinmay Hegde's notes here for a superb 14-minute introduction. And I think this is the way I learned about reinforcement learning. I think it's like very well motivated and with great explanations. Okay, so assuming you've done that, or maybe brushing up, I want to describe the reinforcement learning framework. In this framework, it's very general and abstract, so it can be applied to lots of different situations, many games, the stock market, different optimization choices that we make in an environment. But in all of these different applications, there are some shared elements, the first of which are called states. A state is some description of the environment. So in the Moonlander game we just saw, it's like where we are in position on the screen and where we're moving and our angle. If we're considering something like the stock market, it could be like what the last, however, like 10 days of prices are. It's really quite general and it describes like where we are. It gives enough information to understand what's going on at the current moment. The second part that we have in a reinforcement learning framework is actions. These actions are the choices we get to make. So when we're playing a game, we get to like play with the controls and manipulate our agent in some space. We're in the stock market, we get to buy or sell some securities. If we're in another environment, there's like some associated action which describes the thing that we're trying to do. Crucially, what makes reinforcement learning different from other settings that we've seen so far is there's feedback between the states and the actions. So if I'm in some state, I take an action, that action induces a new state. So if I were playing a game and I moved my character to the right, then that would change the state that I would see at the next instantaneous point in time. And then in this new state, I take another action. That next action again changes the state that I'm going to see next. So there's this complicated feedback loop between the states and actions that we take. In addition to the states and actions, we need to have some sense for what constitutes a good action. That is given to us by rewards. And rewards tell us basically the value of the actions that we take in a state. So if we are playing chess, then when we win the game of chess, we get lots of reward. If we lose, we get lots of negative reward. Maybe if we're in the stock market, the reward is money. So if we win money, it's positive. If we're doing well, that means we're winning money. If we're doing poorly, that means we're losing money. Each one of these setups, we need some way of telling what makes an action good or not. And that's where this reward, the idea of this reward comes in. Okay, so we have states, actions, and rewards. Our goal is to formulate a policy that maps states to good actions as measured by reward. We get to interact with the environment. This is slightly different than the way that we got data before. Before, we had some repository or database where we collected lots of images or captions or tabular data. Here, our data comes from interacting with the environment and learning in a very dynamic way. In this way, we see a particular state, I'll call it ST, where T is denoting what time step we're on. We respond with an action AT. AT is chosen according to the policy that we're trying to formulate. We receive some reward RT, and then we transition to the next state. And the next state is now ST plus one because we move one step forward. We call a sequence of states and actions a trajectory, denoted by the Greek letter tau. So in this case, it's a sequence of S0, so the first action, the first state, the action we take, the next state we see, the next action we take, etc., all the way until SL minus 1 and AL minus 1, where L is the length of the trajectory. We, of course, because we're doing deep learning, we will parameterize our policy with some parameters theta, and we'll call our policy pi theta. This is notation that's borrowed from the reinforcement learning community. Then we'll use pi theta of tau to denote the probability that we see trajectory tau when we follow policy pi theta. What makes this very interesting is that there's lots of stochasticity, there's lots of randomness in our interaction with the environment. So sometimes we get initialized a random state. When we're selecting our policies, at least during training, we select them from a distribution suggested by our policy. And then when we take an action in a state, there's some randomness as to what happens next. So we're playing a game, maybe the level is generating itself. If we're in the stock market, maybe the market responds randomly to the choice that we've made. And then there could also be randomness in the rewards that we get. So sometimes if we take an action in a particular state, the reward that we get depends on some other factor, which we can't predict. And so to us, that looks like randomness. So with all that in mind, that's why we talk about the probability of seeing a particular trajectory, because there's randomness and there's some distribution over this randomness. That's the thing that we're interested in. We're interested in something that does well on average in the majority of cases. Because we want to so let's talk about our loss function. Because we want to maximize the reward, our loss function will be the negative reward for a trajectory. So by minimizing the loss, we're minimizing the negative reward, which is actually maximizing the reward. So when we took action A0 in state S0, we got some reward R0. Here I'm summing all of these up, and that will be the reward that we get for a particular trajectory. Of course, a slight challenge with this is that if we just make this our loss function, then we'll be equally weighting the reward that we get at the end of the trajectory as the reward that we get at the beginning of the trajectory. This doesn't really work so well, because sometimes it's unpredictable. So as we move further out in the trajectory, it's unpredictable, and we can't really tell what will happen at the end of the trajectory. So it doesn't make sense to prioritize the reward there. Instead, we should prioritize the reward of the initial actions that we take now, because we have a higher confidence in their success because of the randomness of the environment. So this reward function is really R of t times gamma raised to the t, where gamma is a discount factor. So let me say that for discount factor gamma. And this discount factor is less than 1 and greater than 0, typically set to something like 0.9. Okay, in this way, we're prioritizing initial actions more than actions down the line. As we said, there are many sources of randomness in the environment, the actions we take, and the reward. So the loss is the expected reward from a trajectory where we take actions according to our policy pi theta. So in this case, I have just put an expectation around R of tau, which says that we're interested in this quantity on average for the particular policy pi theta that we are optimizing over. Of course, in deep learning, the one thing that we know how to do is to run gradient descent on our loss function, but that's a little bit tricky here because it's not obvious how the loss depends on the parameter theta. There's a complicated relationship where we sample a trajectory according to pi theta, and that induces some rewards, which on its surface, this doesn't even look like a differentiable function or something that we could optimize over. Luckily, there's a very nice trick called the log derivative trick, described in Chinmay Hegde's notes, which enables us to write the gradient of the loss as this quantity, which is the expectation of this reward times the derivative of the log of the policy. And I'll briefly show you where you can find this here. Okay. This is the log derivative trick, and I would recommend reading the notes around here for context. It's very nice math, but I don't want to talk about it here during this code demonstration. Okay, so with this in mind, We have all the steps, or almost everything that we need for our deep learning recipe. We have our loss function, we have a network, and we have a method for optimizing our network. There is a little bit more non-trivial work left in how we interact with the environment, but we'll see that in code. So let's jump in. We'll be using the gym environment and a bunch of these libraries. The particular game that we'll be playing is called Cartpole. Cartpole is a fun game that I recommend you check out if you're interested in it. The idea is that we have some cart and there's a pole standing up from our cart, and the pole will fall one way or the other, and our job is to move our cart back and forth to keep it somewhat stable. In this game, the observation space consists of 4 variables: the cart position on the line where we are, the cart velocity where we're moving, the pole angle, and the pole angular velocity, how fast that is moving. So there are 4 variables that describe the state of the space that we're in. Here we can sample that from our environment that we initialized, and we get these numbers. And if we look at the size of these, there are 4 of these. So these are the 4 numbers that represent where we are in this observation space. In this particular game, we can take 2 actions. We can either move to the left or we can move to the right. And we can get that by looking at the action space we see of our environment. I think this game is very fun and actually pretty hard. You can try your hand at it here if you follow this link. You can watch me play it right now and fail. So I need to move the cart back and forth, and my goal is to make sure that the pole does not fall one way or another. If I move it too far to one side, then it'll fall off. And really, I want to keep it balanced here. But as you can see, it's tilting pretty strongly in one direction or another, and I'm in danger, and I think I lost. So if you can beat my high score of 19.7, power to you. I don't want to hear about it. No, I'm kidding. It's a fun game, and the cool part is that there's some non-trivial prediction going on there. When I'm playing it, if I see the pole tilting down to one side, I have to have a sense of where that means it's moving, and then I respond accordingly to get the cart back up there. We'll train a neural network for this task that is actually incredibly simple. It'll only have 2 layers with a dropout and a ReLU between them. As we've done many times before, we'll initialize our architecture in our optimizer, but our loss will be slightly more tricky to compute because we have to take an expectation with this log derivative of the policy actions. So here we just have our policy. Normally we would call it model, but I'm calling it policy today, and our optimizer, which optimizes over these. The input dimension of our network is 4 because that's the size of the state space, and the output dimension is 2 because that's the size of the action space. We described how to compute the single discounted reward of a trajectory above and in class and in Chinmay's notes. Here we're going to be doing something slightly more clever. The idea is that I have some trajectory, which is S0, A0, S1, A1, S2, A2, etc. And it's kind of expensive to compute this because I need to interact with this API multiple times. The idea is that I'm going to define different reward values. So normally I'd call this R tau, but now I'm just going to call this R0. And then I can also get another trajectory from the same one if instead of starting at S0, I start at S1. So if I do A1, S1, A1, the A2, etc., I get another trajectory just for free, and I can keep repeating this. So I'll say R2 is the reward from the trajectory. Really, it's I'll say it's a reward of this trajectory, where I start at whatever the RT thing is. Okay, this is just a very clever method for computing it because we know that R capital T is equal to the sum of everything starting from capital T, the discount factor raised to the T, little t to the minus T factor times whatever the reward we got here is, which I'm calling RT. We compute this thing, and this is our way of maximizing our use of the data so we can learn very quickly. Remember, we want to normalize our reward function. This is because if we add a constant to our reward, such as 1,000, it doesn't actually change the value of the actions in our case, or at least we don't think it should. But because our loss function can be changed if we add 1,000 to everything, that's not so good for us because it would look like from the perspective of the loss function that that's very good. It's negative 1,000, that's awesome. But that's not what we want to happen. We want to have a clear differentiation between good and bad actions. So in this case, we will normalize by taking the mean of our returns and then also divide by the standard deviation. So in this way, we get a good sense of like a good trajectory versus a bad trajectory. And that's what this normalization factor does for us. Once we have these returns and the probabilities of the actions that we take, which we'll get from our policy, so I'm assuming that we're passing both of these in to this function, we will detach the returns from their gradients, so remove gradient information. We can do this very cleverly because of the log derivative trick. And then our loss function is the negative of our returns times the log probability of our actions. And then when we take the gradient of this, the gradient passes through these returns because we detach them for their gradient information. And then we just get the gradient of the log probability of the actions, which is exactly the gradient update that we get from the log derivative trick. Then we will learn as normal where we zero out the gradient, backpropagate through the network, and then take a step forward. With these functions in mind, we can now define our training process. Notice that this is a little bit more complicated than usual. The reason why is because we need to interact with this environment. We'll do that by keep on iterating until the environment tells us that we're done. In our case, the environment will tell us that we're done when we lose the game, or if we exceed a certain number of steps. Okay, so we start with our state. We'll pass our state into our policy, and we get the predictions from this. We'll apply a softmax to it, so we're interpreting the output of our state as probabilities over the actions, which is how much we think the network is telling us to take one action or another in a particular state. We'll turn this into a distribution, and then the actual action that we'll take will be sampled according to the distribution that our policy outputted. And then we can get the log probability of this by using this nice log probability function applied to this distribution defined from the policy that we got to begin with. With the particular action that we selected in mind, we will take that action, we'll take that as our next step in this environment, and then we'll get out the new state that we're in, a reward for action, and then whether we are now done or not. Finally, we will keep track of all the log probabilities of these actions and all the rewards that we computed for this particular trajectory. And then when we calculate the returns, we'll keep all of these in mind for our computation here. And then we'll also, when we compute the loss, we'll pass these and the log probabilities of these actions into the optimizer, and then we will update our policy accordingly. When it's time to evaluate, we'll do something slightly different. The main difference is that we're going to keep track of the frames to be able to visualize what's going on in our game to make it a little bit more exciting and fun. And then the other thing is that when we select an action, we won't sample from the distribution. We'll just take the action which has the highest probability, which means that it's probably the best action that we should be taking. So we take the best action in each step, and otherwise it's quite similar, except we don't do any updates. So let's see how our policy performs before we train it. So this, at this point, is randomly initialized, and this is a video of the performance. It looks like it falls over so quickly that the video is incredibly short. It's like less than a second. So we have a lot of work to do to make our policy better. We're now ready to train. Notice that the very jagged, okay, yes. Now we're ready to train. We'll run it for 600 episodes, and each time I think we'll allow 25 different trials. And then if we get this amount of reward, then we'll stop. We'll run the training code and the testing code, and we'll keep track of both of these and then plot them over time. In this case, amazingly, we actually do quite well. So you may look at this and say this is pretty jagged, which it is. That's actually very common for reinforcement learning because the reward function is pretty sparse. Oftentimes, this is a function or intrinsic property of the environments that we're trying to optimize over. So, for example, if we're playing chess, really the only reward that we get is whether we win or lose at the end of the game, because that's the only indicator that we care about. If we're trying to get out of a maze, the only thing we care about is whether we're able to at the end. So, because of this, there's lots of randomness in whether we get the reward value or not, which is why we're seeing the very jagged performance that we see for the testing reward and the training reward that we're getting here. But it does increase over time, and it looks like we're doing some learning. So let's see that in practice. We now have a video of testing our trained policy, and already we can tell that this is 10 seconds, which is much longer than the video we had before. So let's see if our policy learned how to interact with this environment. It looks like it's doing really well. It like imperceptibly is moving back and forth very quickly as the in order to keep the pole standing up as like close to straight as possible. And I would say that this game has learned a very good strategy for this action. The reason it stopped the policy is because there is a limit on the number of times that we interact with the environment set here. Great. Well, that's all I have for you today. I would suggest that a very cool aspect of this is that you can plug in a different game of your choice from the gym environment, and the code for learning that game is the same. So our approach is agnostic to whatever the environment is, as long as we can interact with it through this environmental, this way where we get some rewards from our actions, and we have a way of like testing our actions interactively through a trajectory. Next week, we will be talking about Q learning, which is another approach for reinforcement learning, which is more sample efficient, and there's also some nice theory and math involved there. Thank you very much, and see you all later.